Hello everyone, I'm Tianliang. I'm a student of Institute of Digital Media, Peking University, Beijing, China. I am currently doing research work on the next generation video coding standard, VVC and AVS3. My research interests include video or image compression, coding and processing, especially video coding standardization. During the development of AVS3, I have co-chaired several co-experiments. Today, my paper title is Hardware-Friendly Interweaved Prediction for Affine Motion Composition. My presentation is composed of 5 parts. First, I will introduce the background of my work, and then the proposed hardware-friendly interweaved prediction for affine motion composition is presented. Following this, the simulation results are reported to validate the proposed method. Finally, the conclusions are drawn and the references of my paper are shown. First, I will introduce the affine motion composition in AVS3. Affine motion composition has been studied for many years on account of its ability to describe complex motions such as zooming, rotation, and so on. In recent years, significant progress has been made in balancing the precision of affine motion composition and its overhead bits. In AVS3, a block-based affine motion composition prediction is applied, as shown in the figure. The affine motion field of a block is represented by motion information at 2 control points with a 4-parameter affine motion model. With this model, a motion vector at sample position x, y in a block is derived as the equation, where MV0 and MV1 are control point motion vectors at the top left and the top right corner. To reduce the complexity of affine motion composition, the MV granularity in AVS3 is at sub-block level instead of the pixel level, as shown in the figure. In order to derive a motion vector of each sub-block, the MV at a certain point is calculated according to the above-mentioned equation. All samples within the sub-block share the MV at the certain point. Affine motion composition is applied to generate the prediction samples of each sub-block with derived motion vectors. In AVS3, the size of the sub-block is set to be 4x4 for unit prediction and 8x8 for bi-prediction. Affine motion composition is efficient on video sequences with complex motion. However, it faces a dilemma to balance the coding efficiency and the complexity, and problems such as uneven prediction quality and prediction discontinuity exist. Motivated by these problems, interweaved prediction is proposed to achieve more coding gain of affine motion composition without increasing too much complexity. With the interweaved prediction, a coding block is derived into sub-blocks with 2 different dividing patterns, as shown in the figure. The affine motion composition is performed twice to generate the 2 predictions with 2 dividing patterns respectively. The final prediction is calculated as a weighted sum of the 2 predictions. In this way, the 2 predictions can compensate each other and achieve finer MVs as a result. The high off-chip memory bandwidth in interweave prediction stems from the requirement of a large number of reference samples. In order to make interweaved prediction more hardware-friendly, the average number of reference samples is proposed to be restricted. The main idea is to restrict the number of reference samples per pixel on the average by accessing all reference pixels at once for one pattern, which means the spatial neighboring subblocks share the reference samples. In AVS3, reference samples per pixel SPP reaches the max value for blocks using bi-prediction with 16 by 4 or 4 by 16 size, and it can be calculated by this equation. Since the affine model is a monotonic function, the reference area that including all reference samples of current CU divided by a specific pattern could be contained certainly in a limited range, of which size is determined by 4 subblocks in the kernel, as shown in the figure. Reference sample per pixel SPP of interweave prediction can be calculated according to the first equation. Here, 7 is set according to the interpolation field size. CUW and CUH denote the width and height of the current block respectively. BW and BH respect the width and height of reference area respectively, which can be calculated according to the second equation and the two figures. To guarantee that the off-chip memory bandwidth required by interweave prediction doesn't exist, the worst case in AVS3, affine motion composition is proposed to fall back to the normal affine prediction when SPP exceeds SPP max. Besides the off-chip memory issue, the on-chip cache bandwidth may also increase due to the affine motion composition for two dividing patterns. The increase in on-chip cache bandwidth comes from the extra access to reference samples for pattern 1 mainly. To reduce the cache bandwidth, it is proposed to fetch more reference samples during the affine motion composition of pattern 0, which can be reused for pattern 1. As shown in the figure, subblock A and subblock B are in pattern 0 and pattern 1 respectively, and they can share the fetched integer reference samples. The width WBB and height HBB of the bounding box containing reference samples shared by subblock A and B can be derived by this equation, where W sub and H sub are the width and height of one subblock respectively. Number type is the type number of interpolation filter, which equals 8 in AVS3. Margin horizontal and margin vertical represent horizontal and vertical additional margin respectively, which are set to ensure that the on-chip cache memory bandwidth is not worse than the original worst case in AVS3. When the subblock size is 4 by 4, margin horizontal and margin vertical are set to 4 and 1 respectively, and the margin horizontal and the margin vertical are set to 6 and 4 when the subblock size is 8 by 8. with the proposed on-chip cache bandwidth constraints. The required integer samples for all subblocks must be within the bounding box. Otherwise, interweaved prediction is disabled for the current CU. For one block in pattern 1, there are 4 candidate corresponding subblocks in pattern 0. The final corresponding subblock is selected from the 4 candidates according to alien top and alien left, as shown in this figure, which are set based on the affine model to maximize the number of reference samples overlapped by the 2 subblocks in pattern 0 and pattern 1. The bottom figures show the cases and conditions for alien top and alien left equal 0. The setting principle is minimize the distance between A and B or A and C in horizontal or vertical direction. The proposed hardware-friendly interweaved prediction is implemented on the AVS3 reference software HPM8 to evaluate its coding performance. All the simulations are performed under the common test conditions of AVS3 with RA configurations. Experimental results in terms of BD rate and time changing of interweaved prediction without and with the proposed constraints are shown in Table 1 and Table 2. It can be observed that interweaved prediction with the proposed bandwidth constraints, the coding gain is 0.45 for Y components. Comparing Table 1 and Table 2, it can be seen that the proposed bandwidth constraints increase the average bit rate a little and have no effect on the encoding and decoding time. Moreover, the number of reference samples required by 1 pixel is used to calculate the off-chip bandwidth, and the on-chip bandwidth is estimated by the number of the reference sample lines. The off-chip and on-chip bandwidth reducing in worst case are shown in Table 3. With the proposed method, 42.3% reducing in off-chip bandwidth and 62% decrease in on-chip bandwidth can be observed, which means the problems of the off-chip memory and on-chip cache bandwidth can be solved in general. This paper hardware-friendly interweaved prediction for affine motion composition is proposed to overcome both off-chip and on-chip memory bandwidth issues. With off-chip memory bandwidth constraints, the required bandwidth in AVS3 in the worst case is not increased by interweaved prediction and reduced 52.3% compared with the original method. The number of accesses from cache required by interweaved prediction is reduced 62% with on-chip cache bandwidth constraints. Simulation results show that the problems of on-chip memory and off-chip memory are solved in general only with a little loss in terms of BD rate. Here is my reference. Thank you.